Bismillah ar-Rahman ar-Rahim. Welcome to lecture number 10 of deep learning. The topic is regularization. The discussion agenda is we will discuss regularization. We will discuss regularization in neural network, and we will see how this regularization helps us to reduce overfitting. This is what we discussed last time. We discussed bias, we discussed variance. Bias is when we have underfitting in our data, and variance is when we have overfitting in our data. And we don't want both. We don't want high bias, we don't want high variance. At the same time, we don't want low bias and low variance. We just want something in the middle with enough bias and enough variance, because both are high bias, high variance is dangerous, and low bias and low variance is also dangerous, because with the high variance we are not able to generalize. With the high bias we are not able to make correct prediction. So this is what we discussed, the like how do we deal with this high bias and high variance problem. So first we check high bias. If there is high bias, then we can try different technique like bigger network. We can try different layers. We can try different neural network architecture. If there is no bias, then we check for variance. If there is variance, then we can add more data. We can add regularization, or we can check neural architecture. And eventually, when there is no high bias, no high variance, so we are done with that. So you see the high variance, we have one is more data. The more data you have, the chances are your data or your neural network will not be overfit. But if you have less data, then chances is that your neural network will overfit to the data. So assume you have enough data, and then you have variance, you have overfitting, then we use regularization. So this is the topic of today, regularization. And what is regularization? So we discuss logistic regression. In logistic regression, we discuss this objective of the gradient descent, that we want to minimize the cost of using W and bias in our logistic regression. And this is what we represent, JWB, and its formula was 1 divided by m. 1 divided by m is average, to take the average of all the sample, and we sum the cost of all individual samples. This is what we discuss in logistic regression. So this is our loss function. Loss function can be anything like mean square error or root mean square error, or the one that we use is binary cross entropy. So we add another factor. This is lambda divided by 2m, and this is w is actually this w, this one, and we use this double bar symbol. It's actually it means regularization. I will discuss this in a minute. So we can do this for W, we can do this for bias, but normally bias, the contribution of bias is very minimal, so we can actually remove this. We can only focus on W. So this lambda is regularization parameter, lambda, and this is lambda, we actually write like this, but in Python, lambda is a symbol, and so lambda is used for different purpose, so that's why we have lambd, lambd. Okay, so lambda divided by 2m. So divide by m is actually to take the average, and divide by 2m to further reduce its value. So what does these two means? Actually, if we open it, it's the sum of all w squared, and the squared is taken as w transpose w. So we sum all the w, we multiply all the w of all the, well, there is only one layer in logistic regression, so we just multiply all the w together. So normally the value of w is very small, like 0.1, and we multiply 0.1, 0.1, it becomes 0.01. So it actually reduces the effect of w. And so this is L2 regularization, where we do not divide this W by anything, and L1 regularization, where we divide this lambda divided by 2m and W. And W will be sparse. After this operation, W becomes sparse. And how does it help us to reduce? We will discuss this in 1 minute. So that was logistic regression, and in neural network, we have this loss, this function of W and B, and we have L. So W1, B1, W2, B2, up to WL, BL, and we take the sum and we add this factor of regularization. So this is the sum for L1 to L and WL, and this 2 and this F. F means Frobenius norm, and the formula of Frobenius norm is this one. So we sum all the W for all the layers. So for 1 to L, and then for L minus 1, and we sum all the W, the square of the W. So this is Frobenius norm. And remember to add this in the back propagation step as well. So the derivative of WL from back propagation is a value, and we add also this regularization term, lambda divided by m WL. Okay, so if we open this, so WL becomes WL minus alpha. So this is for the update rule. So we get this DWL. DWL is coming from here, and we update W. And if we open this formula, so dW from back propagation value plus the regularization term, and if we open it, so then it becomes something like this and like this, and if we take common, so it becomes WL minus alpha, this. So we are adding actually this value, and this value is less than 1 because it is 1 minus a large value. And alpha we discuss is a learning parameter, and lambda is regularization parameter. So how does it help us in reducing overfitting? So we are making the value of W very small, is approximately equal to 0. Lambda is normally a large number, and this Frobenius norm makes the values of W closer to 0. So those values that are very small, they will become even more smaller, and their effect will be very minimal, or will be reduced completely. So this is what we discuss high bias, this is what we discuss high variance, this is overfitting, and how regularization help us. So there is a weight assigned to this neuron that is making this classification, and we make that weight closer to 0. So then the line become like this, and similarly for this one we make it closer to 0. So actually this is what the neural network framework. So we have different weights, and the certain weights becoming 0, like this weight is becoming 0, this weight is becoming 0. 0 means their effect is very minimal. So for one iteration it is taking this one, and in another iteration is taking a different value, because we are computing this loss for one iteration plus regularization, and then for the next iteration we take different values. So this is how it helps us to reduce overfitting. If we look to the sigmoid function that we are using, so then this is our sigmoid function, and you know the derivative here is closer, this is actually 10h function, sorry, because sigmoid start from 0. So 10h is from -1 to 1. The derivative here is closer to 0. The derivative here is closer to 0. Only here it's a value. So if z is very small, then the 10h function will be linear, as in linear regression. So depend on this z value, whatever is this z value, it will be linear like this. because we want it to be linear, because here the derivative is closer to 0, we want it to be linear. So we want to make it so lambda very high, weights goes down, and eventually the value of z becomes small. And when z becomes small, it works like a linear regression. So very large approximately means linear. So this is our Frobenius norm, and it helps us to reduce the iteration. Like we are per iteration, we are reducing the cost, and eventually we will see that, well, these very fine details, they are simplified. So that was regularization. I will upload a paper about regularization. Please read it. Thank you very much.